Okay, so here's the first notebook, Python Mysteries Unveiled. And the first thing I want to do is just review something. I don't know, I'm sure there are some people that know all this stuff really well, and so I apologize to you, but there may be some people who could use this as a review. So I'm going to just go through and define a little class, which is called regular card, and it has two attributes, rank and suit. So rank is the number, is the identification of the card, and by its number or rank, and suit is the either diamonds, clubs, hearts, or spades. So and so we've defined a method in here to initialize the class, and then we've defined another method that that allows you to compare this class to an object that you've created by this class to another object and see if and test for equivalence. And then we've also defined this method called REPR, which is supposed to produce a machine-readable string that describes the object. So let's just run this thing, and then the Dunder attributes, that is the ones with double underscores, are not meant to be accessible from outside the class, although they still can be accessed from outside the class. It's just that they're meant to be internal variables. The thing I like about Python is it doesn't enforce this. In other words, even though they're not meant to be accessible from outside the class, you can still get at them from outside the class. So I'm going to define an object called card, and it's going to be regular card, queen of hearts. So it's basically representing the queen of hearts. And then we'll see what its attributes are, and you call the attribute by card.rank and card.suit. And so there they are, rank Q. So there's this method also that the way to get at the attributes, there's this method called getAttr that all objects have. You don't even have to do anything. It's already an intrinsic method. So you can get the rank this way, another way to get the rank, and another way to get the suit is you could do getAttr card suit. And then another method that you have accessible, which all objects have accessible, is this setAttr method. So by doing this command, I'm going to change the card to a jack of hearts. And the way to do that is just to use the setAttribute function method. It's a method that's accessible to all these objects. Set the rank attribute to jack. So I'm going to do this. Now we should have. We can now see what it says when I call card. We'll see what it says. And now you can see we've changed it to a jack of hearts. And now we can use this equivalent method to see to test some equivalences. So I have here I'm cheating. I'm accessing this equivalence method from outside, and let's see. So the card I have, remember, is jack of hearts, and I'm going to ask if it's equivalent to queen of hearts. So the first answer is false. Then I can also ask if it's equivalent to jack of hearts, and it's true. And then I can make another card object. I'll call it card 2, which is, instead of a regular card class, it's just a list of jack and hearts. And then I can ask whether card is equivalent to this newly defined card. And so you can see what happens. In the first case, as expected, the queen of hearts is not the same as the jack. The second case, the jack is the same as a new object with jack of hearts. And in the third case, it's comparing it's comparing an apple to an orange, and so it says not implemented. That's what it's supposed to do, as you see. If the other class is not the same, then if you're comparing two different classes, then it says not implemented, and that's what we're doing here. Because in the one case we've got a card, in the other case we've got a list. Okay. And then this is what the repr attribute gives. it turns out that the repr attribute is already an intrinsic method, so that you can ask for repr. We defined repr on card one on the card method. Sorry, on the regular card class, but we didn't define anything on the list class. And it turns out that list class already has an intrinsic repr defined, so you can actually get this representation that shows you what's going on in this list. And then the class attribute returns. It's also an intrinsic method, and it tells you what class you have. So the card that we defined is a regular card, and so it gives us that class. But this card 2 is just a list, and we see indeed that when we ask for the class of it, it says that it's a list. Okay, maybe I'm beating a dead horse, but anyway, so if a good way to see all the attributes of an object is to do a dir on the object. So I can do that, and you can see there are all these intrinsic methods, including this ones that we use, the set attr and the get attr. I guess get attr is something we didn't even see. I think get attribute calls it. And then you see it's the actual properties that are meant to be seen externally, and that is the rank and the suit that you can get at by just going card.rank and card.suit. And card 2, being a list, also has a whole bunch of intrinsic methods that are defined, and it's interesting. It has a lot of methods, a lot of extra things that we don't see in the regular card class. You see there's this append, pop, remove, reverse sort. These are all attributes of list. These are all methods that can be used with list. So that's just something to see. Okay, the second thing is this. Okay, I'm going to stop here, pause, and see if there are any questions. Does anyone have a question up till now? Or in general, any general question? Because we didn't really have a chance to sort of warm up and start that way. Okay, no questions up till now. Shall I proceed then? Okay, so the next thing I wanted to talk about is this this Starargs and TWiML that we always see in the Fast.ai code, and indeed in a lot of Python code that's a little bit more advanced. And these are really interesting features of Python language. They let you pass variable length keyword and non-keyworded variables into a function, respectively. The Starargs is for non-keyworded. I got this backwards. So yeah, the Starargs is for non-keyworded, and the KWRs is for keyworded. That's what KW stands for. Keyword, keyworded, and non-keyworded. Okay, now that's correct. Okay, so I wanted to demonstrate this for you so you'll really understand it. Sylvan says, Sylvan Guger, who's been helping develop the Fast.ai library, he's the main force behind it, actually, in addition to Jeremy. He gave a really concise definition. And he said that star is to unwrap a list of non-keyworded, a list which is non-keyworded arguments, and star is to unwrap a dictionary, which is keyworded arguments. But note that the prefixes star and double star are valid only within the argument of a function. You can't reference them anywhere else, only inside the argument. And they're used to pass objects into that function. So let's do a little example here. I've defined this function called func, and what it does is if there are any arguments, then it prints them, and it tells you how many there are. Otherwise, if it says if there are no arguments, it says there are no non-keyworded arguments. If there are keyword arguments, it prints them, and it tells you how many there are. And if there are no keyworded arguments, then it says there are no keyworded arguments. So now I'm going to give a few examples of how to use this. So I'm going to define a list of non-keyworded arguments, and then I'm going to define a dictionary, which is keyworded arguments, right? Because dictionaries have keywords. So I'm going to define an input list and an input dictionary, and then I'm going to call this function with the input list and the input dictionary. And but the way so notice what it does. It says it returns a list of arguments, and the arguments are the list and the input dictionary. And it says args has 2 elements, and it says there are no keyworded arguments. And the interesting thing is that the input dictionary is a dictionary, and so it has keywords. But in this case, it's only considered as part of the input list, and that's because you're not explicitly specifying the keyword arguments. So now let's try something else. Suppose we define an input list, which is random numbers from 1 to 5. Random numbers chosen, 5 random numbers, Gaussian, and an input dictionary, which says zebras, 14, giraffes, 3, and an input list, another input list, which is ABC. And let's provide those lists as inputs, and then see what it does. Now notice how we're supplying the input list. We're supplying them as keyword arguments. I1, I2, and I3 are being supplied as keyword arguments. And so the way this thing returns, it says there are no non-keyworded arguments, but the keyworded arguments are I1, and it gives you the value, which is the 5 random numbers, I2, which is the input dictionary, which is the zebras and giraffes, and I3, which is the list of ABC. So that's when you're calling the function only with keyword arguments. Is everybody up with me now at this point?
I think so. Okay. So if you had called the function without, the keywords, would it have behaved differently?
Yeah, we did that
taking
up
out
here, right?
I1. Right.
Yes, exactly. Maybe that's what I should have done with this example. Let's do that. That's a really good idea. So I'm going to do what Christine suggests. I'm going to put this down below, call the function again. But this time, instead of calling them out as keywords, I'm just going to supply them as variables. And now you see that exactly what Christine expected has happened. It now thinks these are non-keyworded arguments because I didn't specify them as keyword arguments. Because you see, this is the way you specify something as a keyword. You give something, keyword equals value. But here I just specified them as lists, and a list can have a dictionary in it. So even though there's a dictionary in there, it's treated as a non-keyworded variable, and that's exactly what happens. You have 3 elements in args, and there are no keyworded arguments. And now I'm going to show what happens when you do a mixture of keyword and non-keyword arguments. Here I've supplied the input list 1, input list 2, and then input dictionary equals. So I've supplied, this is a non-keyword argument, keyword argument. And so now it's going to say, you've got 2 args, and it tells you what they are. They're the first 2 inputs, and then the keyword arguments is that input dictionary, and it has 1 element. Now, the thing to note here is that in the case of mixed input, the non-keyworded arguments must precede the keyworded argument. So I'll show you what I mean. Suppose I try this again, but I change the order. And I put this keyword argument somewhere in between. Not at the end. And now, it took that. That's funny. No. Oh, sorry, I didn't do the right thing. I didn't copy the right thing. Hold on. What I wanted to do was mess around with the order of this one. So I'm going to give the same command, except I'm going to change the order and put this argument after the keyword arguments. Okay, so see, I've got a non-keyword argument, and then a keyword argument, and then a non-keyword argument. And what it does is it chokes. It says that you've made a syntax error. The positional arguments follows the keyword argument. That's referring to this one. See the arrows right there. All of the non-keyword arguments, they call them positional arguments. They must be before the keyword argument. So that's what I mean here. Non-keyword arguments must go before keyword arguments. Right, so that's just something you have to remember when you try to input keyword arguments. Mix keyword and non-keyword arguments. The non-keyword arguments have to come first. Okay. Any questions up to here? Okay. Then here's another thing that baffled me when I first saw it, and I'm sure if it baffled me, there might be some other people that might want to know about it too. So you see in a lot of this material in Chapter 9 and Chapter 10 where he uses this super method inside of a class. And what this does is it allows you to inherit from a parent class. That's what the super means. So let's define a parent class that has that can take as inputs X and Y, but when it gets them, it just goes, oh, somebody asked a question. Jess, is the point of keyword arguments just for clarity by using a name for the argument that is easy to understand when reading the code, or is there more to it? Let's see. That's a good question. Let me think about it. This goes back to something that I wrote in that little note on software engineering that I talked about last time. And that is like, if you see a function called with inputs, 3 and false, if you see the function called that way, you don't really know what the inputs are doing. But if you name those inputs with keywords, then when you call the function, you call the function with number of iterations equal 3 and try this equal false, then you've named then people can sort of understand what those values of 3 and false are representing. And so it's just clearer that way sometimes when you write code, so that when somebody sees a function called, they don't have to go into the function and figure out, oh, what is this 3 representing? What variable is the 3? What variable is the false? So naming the arguments as keywords, just for me, it's for clarity. There might be other reasons, which I can't think of right now.
It helps you pass basically arguments to the next function that you're calling within that function, like how Fast.ai does. You call a function, whatever is in quarks basically gets called to the next, gets passed directly to the next function that you call within it, and it kind of gets chained like that, one inside the other, inside the other.
Yeah, and also Jack says it lets you set defaults, and that's right too. So you might want a variable in your function that people are going to eventually change, but you might initialize it to none. So you might call a function with x equals none, and then later on somebody can call the function and change x by giving it a different value. So yeah. And let's see. I don't know, Jeff, could you ask the question? I see your question, but I'm not quite sure what you mean.
Yeah, you would have to scroll up so I could kind of give you an example.
Oh.
But like
okay.
like so for example, you've got the input dictionary and you've got zebras and giraffes or something like that. And so it just seems like you could name that like zoo animals or zoo dictionary or something. And then you would not need to use the keyworded argument to pass that in a way that would be clear about what it is, right? Like if I named it zoo dictionary and then I want to keyword it zoo animals, it's just kind of like, I think we already got it from the initial naming.
Yeah.
So
yeah, that's true. That's true. So this one here, right, input dictionary, you said call that zoo dictionary instead.
Sure,
then,
or just to use an example, like the random 5, so it's like random list or something like that, and then you could not need to do the keywording. So that's why I was just trying to figure out, is there some other benefit or advantage in terms of how the keyword arguments function, or is it just purely for clarity's sake?
I think there's more to it than that. I think that it's a powerful construct that can be used for more than just clarity. So, like for somebody already mentioned that you could initialize something. You could initialize using keyworded argument. You can initialize something to none, just for a placeholder, and then you can later on change it. But then at least they would see when you call the function that it has this value that can be set, that you've set it to none as a default, but you can change it by calling the function with a different value. Does that make sense?
No, because I don't understand why it would have to be a keyword argument in order for you to be able to do that.
Oh, okay. Well, let me think about that, because it doesn't occur to me now, but I will think about it, okay?
Okay, thank you.
Try to think about it. But I'm pretty sure, I'll get back to you on it, but I'm pretty sure that there is, it's a very powerful construct. It's for more than just code clarity. There's a lot more things you can do with it than that. Okay, but I'll think about it and get back to you on it. All right, so back to the use of super. Okay, so I've defined this parent class, which initializes itself with X and Y that you give it, but then it overrides those values and just initializes them to zeros. Okay, and then it passes. And then I've got this subclass that inherits from the parent class, and this time it takes the values that you give it and it initializes X and Y. And then I've got that's subclass 1. Subclass 2 inherits from the parent class, but this time it first initializes to X and Y, but then it calls this super method to initialize from the, and what that means, it says initialize the X and Y from the parent class. So let's see what happens. First I'll define the function. Then first one, subclass, uses its own init method, and when you when you look at it, so I'm defining Z1 as an object of subclass 1 with X1 and X equals 5 and Y equals 10 supplied to it. And then I'm asking to print the X and Y properties, and they're 5 and 10 as you expect. Then subclass 2, super.init is used to override the native init method with the init method inherited from the parent class. So exactly what you would expect according to that sentence happens. Subclass 2 first initializes itself. This is kind of a dumb example, but I just wanted to show you what the init does. So it first initializes itself the way, the normal way, by just setting self.x equals x and self.y equals y. But then you call super init, and that overrides it. And so what happens then is that it goes back up here and says, what does my parent class, how does it init? And then it says, I'm going to do it that way. And so instead of returning x and y, it returns zeros. Does that make sense to everybody? It overrides the init method with the one from the parent class.
Joseph, the overriding is happening because you're calling super after init, right? In general terms, we'll usually have super called before init. So you'll call super so that it inherits from the base class, and you'll get default.
Oh, that's a good
and then
point.
You will try to
now, yeah, let's try that. Let's try that. Yeah, that's why I thought it was a dumb example. So I'm going to, let's see. What if I have two more variables? Let's see. Okay, so you're saying I should call init after that.
Usually super is outside def init altogether. So it's not even
outside def.
Right.
Okay, right. Okay, so we'll do this. We'll do the super init x, y, and now we're going to init A and B. We'll add two more properties to our code like this. and self dot a b equals a b. Okay, so now what do we expect to happen? If I call this, I'm expecting that my new object of subclass 2 is going to have properties x and y, which are going to be 0, and then it's also going to have a and b, which are whatever I give it. So let's try that and see if that works. So I'm going to call subclass 2. Sorry. Call subclass 2. C. And subclass 2. And I'm going to go a equals 5, b equals 10. So this is what you suggested, right? I mean, I'm going to first initialize it by inheriting from the parent class, and then I'm going to add some new variables to it. So I've extended the class. I think that's what you meant. Oops, now it doesn't like that. Super has no arguments. Oh, super init xy. Super init xy. What if I just go super init like that? Because maybe it'll already know about the x and y. Nope, it doesn't like that either. Super has no arguments. If I go x, y.
It's a typo.
Well, I could just give it some arguments. X equals 21 and y equals 15 and see what happens. Oh, didn't like that either. No
You're calling subclass 1 instead of subclass 2.
Ah, right. Yeah, there you go. So let's see what happens if I do it the right way. Okay, and it got an unexpected keyword argument A. Why? Subclass 2. Oh. I'm just going to do that.
Yeah, please try to put the super init inside the init. I don't think it's true that you can put that.
I'm sorry, can you say it again?
Could you put the super init inside the def init? Because I don't think that's right. What was suggested by someone.
Oh, okay.
It's correct that you probably call this first, but don't call before. No, before the.
Okay. Okay. Yeah, I think that's right. Yeah. So because the init method is supposed to be.
To pass on all four variables: a, b, x, and we. You.
You think? Let's see. Let me try that. I think let's see what happens. It's missing required x and y. Okay, so you're right. So if I go init self x, y, a, b, and let's see, it'll know how to get the x and y from the parent class. Nope. Super init. X, y. See if it does that. Nope. Let's see. It is missing x and y. Oh, init is missing x and y. Super init. I'm confused. So super dot init. In fact, I always thought super init you don't even need to call arguments because it has them already. It knows from the parent class. Oh well, this is going to have to be worked out later. Okay, I'm gonna move on so that unless anybody has any ideas what went wrong here.
Yeah, I think
we're trying to demonstrate.
You have to go to when you call the subclass 2 in the next and then you have to add something behind this for x and y and just give it any value and it should be working.
Okay, so x equals 21.
Yeah, perfect.
Y equals 15 and see what happens with that. That might be it. Let's see. It still complains. And it is missing required positional arguments. Positional arguments. Okay, then I'll just put in like this. It's expecting positional arguments. Nope. Still super init. so it says init is missing 2 positional arguments, x and y, but I'm not sure why. Super, what if I did this? I don't think it's going to work. Anyway, I'm running out of time, so I don't want to spend too much time here. Nope. Okay, we'll figure this out for next time. Okay, unless somebody has a quick idea. Oh, somebody says, Jack says, I think super init is normally inside the definition of init. So super init is inside the definition of init. We've done that, right? Super init xy. Super init xy. Okay, so you want super init x like that, right? Normally inside of init. Okay. Okay, well that did it. Now let's print out z1. Oh, well, I'm going to ask for z1.a, and that's 5. That's why we put it there. z1.b is 10. z1.x, what do we expect for x, right? Since it's getting x from the parent class, we think that x should be 0, and it is, and y is also 0 since it's gotten from the parent class. So this worked according to what Jack said. So thank you, we fixed it. All right. Okay, and then finally, there's this thing which I've heard Jeremy talk about it. It's called closures, and I didn't know what it was. So I spent some time looking it up online, and closures are, it's kind of weird. There's this really interesting, beautiful description here that says objects are data with functions attached. And think about it. You define a class and it has methods, and those are the functions. So a class usually has data in it, and then it has methods to operate on that data. You can pass in the data, and then the methods will operate on that data. So that's the first phrase. Objects are data with functions attached. And closures are the opposite. They're functions with data attached. So you define a function that already knows what data it's going to operate on. And another statement I found is that a closure is a function object that remembers values in enclosing scopes, even if they are not present in memory. So that's basically saying again this: closures are functions with data attached. The function remembers some data that it has from its enclosing scope, that is from the function that's outside of it. So here's a simple example of a closure, and it's making use of this Python 3 method called non-local, which defines. Okay, so we first say we define a function called makeCounter. We initialize I to 0, and then inside makeCounter we define counter with this non-local variable I, and then the counter increments I, and then returns the incremented value of I. But then that function is inside here, so you can say that it's enclosed inside. This function is enclosed in the makeCounter function, and the enclosing scope is so the enclosing scope is the scope outside of counter. Okay, so what do we expect to happen if we make 2 counters? Let's say C1 is makeCounter. That's going to be one counter object, and C2 is going to be another counter object, and then we call these counter objects. So we're going to call C1, and then we're going to call C1 again, and then we're going to call C2, and then we're going to call C2 again, and look what happens. The first time we call C1, it increments the value of 0 and returns 1. But the next time you call C1, this C1 object, remember this is a C1 is a closure now, and and it remembers, because of this non-local scope of I, it remembers that last time it saw I was equal to 1. So it ignores, when you go into make counter for the second call, it ignores I equals 0 because inside of counter it's referring to the non-local I, that is the one that's already been incremented to 1. So now it says, okay, the I is 1, I'm going to increment it to 2 and return that value, and that's what happens here. And then C2 is a different counter object, and so when you call it the first time, it also returns 1, and you call it the second time, it returns 2. So that's an example of a closure. Okay, and so that's the end of this first Python Mysteries Unveiled. I'll go to the next one, which I'm going to try to explain decorators and also the debugger. So first we'll go to decorators, and here's a reference on decorators. First of all, can everybody see my my screen? I want to make sure that it's still sharing what I think it's sharing. Philip, are you seeing the decorators?
Yeah, I can see it.
Yeah, I can see it.
Okay, great. All right, so first let's define a function, square, and then we'll call the function, and we know what's going to happen. It's going to, we give it 5, we pass it the value 5, it squares the value and returns. Now let's decorate the function to modify its operation. This functools thing is something I'll talk about later, but let's pay attention to this myDecorator function. So a decorator takes a function as an input and returns a modified version of the function as an output. It returns a function wrapper as an output. So it takes whatever function you give it, and then it prints. So then we're just seeing what's happening inside of this wrapper. Now here we're using this formalism that we talked about, the Starargs and KWRs, to make this really general. That is, we don't have to specify what inputs and outputs the function takes. So this is partially an answer to Jess's question, is there more use than just making clean, pretty code? This allows you to be very general about what function you want to decorate. It doesn't care right now that you're decorating the square function. It'll take any function and perform this. So the wrapper is going to tell you something, is going to print something is happening before the function is called. It's going to warn you that you're about to call the function. Then it's going to call the function. It's going to tell you what the name of the function is, because that's this. And then it's going to give you the result of the function, of calling the function. And then it's going to tell you that's what the function's been called, and this is after the function is called. So so let's parse this thing. Oh, and the functools, this thing is just some mysterious incantation that helps that allows the decorated function to remember its original name and documentation string. So we'll see what that does in a minute. So now I'm going to call the decorated function. Square equals myDecorator square. So we're modifying square by using this decorator. And so now we've basically defined this new function square, and now we're going to call it. And so now, instead of just returning 25, it prints this line, something is happening before the function is called, function name is square, the result is 25, and then it says after, this is basically telling you the function's been called. So you see you've modified the behavior of square by, quote unquote, decorating it with this myDecorator function. Now, now let's suppose I take away this functools line, right? I'm going to do the same thing. Oops, I have to initialize everything again because it remembers stuff. I'm going to have to restart the kernel. Okay, do this, do this. Oops, I forgot to, I have to define square first. I do that. Then I do this. Then I do this. Call the function. Oh, it still remembered its name. I thought it wasn't going to remember its name. Okay, I thought it wasn't going to remember that its name is still square. Sometimes it returns. Well, I've seen before where it returns the name wrapper instead of square. Anyway, oh, let's try this. So now I have this new function square, and yeah, instead of knowing what it is, it says that it's a wrapper, and then when I call its name, it thinks that it's called wrapper. So let me go back. I'm going to initialize everything again. I'm going to call this function again, but this time I'm going to put the functools line back in, this magical incantation, and does the same thing as before. But now, when I ask for this representation string, oh, okay. Well, it still says it's a wrapper, but then when I ask for its name, it knows its name. So at least that's what this functools thing does, is it makes the function remember its original name rather than the wrapper's name. All right. And then finally, so this is all that, this is a decorator, okay? This is what a decorator is. But now there's this, what people call syntactic sugar. It's a nice syntax that is a, I don't know, a compact way to do this. So instead of saying square equals my decorator of square, you just put this @ at my decorator. That says we're going to take my decorator and pass it the following function, the function that is immediately following it. So now this accomplishes the exact same thing as this, as square equals my decorator of square. So some people say it looks prettier. So yeah, I mean, actually, it's not just this line, it's the function definition line too. So it's this line, it's the definition of the function plus this line. And it's accomplished here, the same thing. So now when I call the decorated square function, I get exactly what happened before. And name, it remembers name, it remembers its helper, it's a docstring, because I put a docstring in there, I think. Let's see. Yeah, I put a docstring in there. So when I ask for help, it gives me the docstring. Okay. And I think that's another thing, that if I didn't put this, if I didn't put this functools line, it wouldn't know it wouldn't know how to get to the docstring. So let me try this again. Initialize everything. Sorry, clear. I define my decorator. Then I go down here and call it. And now I ask. We already know that it remembers its name now, but now it doesn't remember its decorator. Sorry, it doesn't remember its help. It doesn't remember its helper. Well, the documentation, the docstring, right? If I didn't use the functools, which that's what I did, I commented out the functools. Now I can't get to the help function. It gets confused because it thinks that we're dealing with wrapper. Okay, so that's all that was. Okay, secondly, in this thing, I want to talk about the debugger. Anybody has any questions so far? Okay, so I see a question from Srinivas. Oh, Vishwas says, Jack has a question here. What does the exclamation point R mean? Well, that's something I just learned too. The exclamation point R removes the, let's see, where are we? Let me find it first. Okay, so let's go back and do this again and see what. Restart. I'm going to do this, and I'm going to call that function. Oops, sorry, I forgot to define square. call the decorator function. And let's see. So func name exclamation point R. I believe that gives you these quotes. So let me show you what happens if I don't use that. Yeah, sorry, let me initialize everything because it's confusing when it remembers what happened before. So I initialize everything again, define the square function, define the decorate function, but now I've taken away those the exclamation point R after the function name, and then when I call this thing, see now it says function name is square. So it doesn't have the quotes. So that's what this this thing did. The exclamation point R, it puts it in quotes. That's all it does. Okay?
Okay,
so,
thanks.
Yeah, so let me just make a comment here. All right, let's see. Okay, next question is decorator function working because of @functools.wraps? No, the @functools.wraps is just a little bit of that makes it a little bit nicer. This thing helps it remember its name and its documentation string. That's what this @functools.wraps does. Okay, without it, you still can have your decorator. It just won't remember its original name, the original function name, and it won't remember the doc string. Okay, so that's just a little magical incantation that helps, but it's not necessary. Okay, let's see now, another question. Okay, okay, somebody says, Srinivas says, that is because in cell 5 you have renamed my decorator to square. If you just call my decorator in cell 5, the name would not be square. Cell 5 call. If you call my decorator, it needs an input. Okay, right. You can give it anything as an input. So I can define another function. So let's do this. See, now I could, this is one of the cool things about decorators, because now I can do this. I can decorate with the decorator that I have. I can decorate any function, so I'm going to decorate cube. So let's do that. And now when I call cube, cube has been decorated, so I'm not going to get the original cube. I'm going to get the decorated cube, and there it is. Okay. Now I'm going to read from the comments. So Rekil Prashant says that one of the common ways to use it is if you kind of want to wrap some other class or object, then you can take a bunch of stuff as TWiRGs and pass it off to some other function or object. Not great as an API. Other usage, we're going to allow the user to create 2 callbacks, different number of parameters. Yeah. Okay. The @functools wrap, I'm looking at Srinivas's comment, only helps renaming the wrap function to have the original function name and retain the doc string. Yeah, that's what I said. So yeah. So there's that. Now let's look at the debugger, because somebody asked for an example of that. So there's this function, and there's this built-in function in Python called PDB, the Python debugger. And so to get access to it, all you have to do is import it. And then to use it, you just do pdb.setTrace inside of the function. That activates the debugger. Now, up here, I've just copied a web page that I found listing all the debugger commands. But really, there's a few that you want, that you use most commonly. And that is S for stepping into a function, N for next command, R for return. You just keep going till you find a return. You just keep executing the commands until you hit the return and then return. So N is the next. Okay, let's just go through some of the common ones. I'm going to stop. So more advanced is you can set breakpoints. We won't do that this time, but you can set breakpoints to have the execution stop at the breakpoint. I haven't looked at down D and U, down and up. Some people might know what they do. H for help. So these single letter commands are the most useful ones. Then S for step, it executes the current line, stopping at the first possible occasion, either inside of a function that is called or on the next line in the current function. So we'll see how that works in a moment. N is different than step because in N, it also continues the execution, but if it happens to land inside of a function, it completes the execution of the function and exits. That's the difference between N, next, and step, and S for step. If step happens to execute a function, it will stop inside the function. So that's how you can get access to the internal scope of functions, by stepping into them. And then R, return, continues the execution until the current function returns. So if you do get inside of a function and you start stepping inside that function, and you've seen what you want to see and you want to get back out of that function, you can hit R, and it'll just go down until it finds the return in that function and gets you back out. C for continue, it continues the execution, only stopping when a breakpoint is encountered. Remember, you can set breakpoints with this B command up here. It's up here somewhere. B for break. And with break B, you have to refer to a line number. But let's see what happens, what I mean by line number. Then jump, J, jumps to a line number. L is a useful command because it lists the source code in this current file, 11 lines around the current line. So it's useful. And then A for args, it prints the argument list of the current function. So let's see how this all works. And Q for quit, okay? So I'm going to import the debugger. I'm going to generate a random data vector. And then I built this sort of a stupid function to compute the root mean square of the data, okay? So I've got this root mean square function, and inside of it, I call the debugger. And then I have defined all these three little helper functions, one to compute the square, one to compute the square root, even though I don't need that because we have access to the square root, and one to compute the mean. And I compute the mean in a dumb way, just so I can step through it and so on. So, and then after defining these helper functions, it does the computation. Mean square equals mean of square, okay? And you can see that this is a bug. I put it in here on purpose. Square needs an input, right? It needs to have an input, and I called it without an input, so that's the bug. And then RMS is going to be root of mean square. And then it's going to return the root mean square. So let's call that function, see what happens. So what this does, since I set the trace and I called the debugger, I'm now inside of the root mean. I'm now inside of this root mean square function. And to see where I am, I'm going to hit list L, and it tells me where I am. So it tells me I'm right inside the function at the very first line. So it's defining the square. So I can now like step through it by N. And now where am I? I can do L. I've stepped through the square definition. Remember, N steps into a function, but it continues until that function is done. So that lands me at the next function, and then I can do again N. That gets me down to, we expect I'm going to be at the third helper function. And there I am. I'll step through that. N. And L is going to list where I am. I'm going to compute. This is where I expect the error, right? So let me see. I'm going to say A for arguments because I think I should see. Yeah, it tells me the input of the function, right? So inside the function, I now have access to X, which was the input argument. Go back up and see what that makes sense. Okay, so I called this function Rootmeansquare. I gave it the data that I manufactured up here, and so inside the function, inside of Rootmeansquare, I expect I should be able to have access to that data, and yes, I do. All right, so next let's do the next line. Should I do S? Yeah, I think I'll do S. I'm going to step, and it returns an error, square missing one required positional argument. But where am I? Let's see. I am. Oh, I'm still here. It just found an error. So now I'm going to give it. I'm going to correct it. Well, I can't. Let's see. Is it going to let me step next? No, it won't let me get past her. What if I go return talk? No, it found an error and it's not letting me get by the error. So anyway, I see what the error is. It says square missing one required positional argument, and then I can go back and correct it. And it should be Rootmeansquare. It should be mean square of X. So correcting it like that, and now it finishes. But why didn't it? Oh, it's in. I have to initialize all this again. Okay, I've corrected the function. I'm going to run it again, and now I expect again. I expected to see the debugger inside the function, but it didn't. It worked correctly. I should make sure that I got it. Oh, data defined. Oh, I forgot to what I did. Just do everything. I initialized everything. I restarted the kernel, so I've got to do this. Oh, and it did, and it does give me the debugger like I expected. So let's see where I am. Now I can step through again and see where I am. Okay, now I can do this S thing. I'm going to step into the function, see where I am. I stepped into this line here. So it took me inside of, inside of mean. I guess mean then calls the square. So now I can step again, and I should be inside of square. So L for list. Yeah, I'm inside of square, and I can ask for, let's see, I think there's a way for you to ask for, yeah, A for args. So I'll see what I have access to in here. And so inside of square, I have access to the data X. I can do next, which will complete that and take me back, or R. That will take me back. So now where am I? I'm returning. Let's see. I want to continue. That's what I want to do. Continue to get out of this. Okay, so I think now I'm out of it. Now I can print, and that would be the Rootmeansquare of my data. It's kind of weird because my data should have an RMS of 1 or of 2. Huh? Oh, square root. No, I don't know. Try this again. Start the kernel. Oh, it's stuck. So it's in the debugger, and I want to exit so I can go Q. And why doesn't it like that? This time, it didn't get R because it didn't finish. Okay, I'm not sure what happened there. Why it?
You don't use Q there. You want to use E. You want it to finish
you
running.
You want to use what?
Code.
E means you said E.
C as in cat.
Oh, C as in cat. Okay. Okay. Well, anyway, I just noticed that I'm late. I need to leave so that people can get to the next class. But I did get through these two, but I didn't get through, and we already did half of 5A last time. And so I guess next time we'll continue with 5B. I think we even did part of 5B last time. So we'll continue, and the goal next time will be to get through the rest of the 5 ones and also the 6, and see if we can get into the 7, because there's only one more after this to finish chapter 10 is notebook 7. Anyway, any questions so far? I'm sorry I didn't get as far as I wanted. I'm just doing all this preliminary material because I think it's important to keep everyone up with us so that people don't get lost. Because there's all these things that happen in this software engineering stuff that people even people who have some coding experience might not know these things. And I think it's important that people see these little bits of Python that we're exposing here, so that they'll have an easier time with the code that is being developed in the Fast.ai library. Anyway, yeah. Well, thanks for your attention, and we'll see you next week and continue on chapter 10.